Hi, Dan Fleisch again, and this is the introduction to Chapter 4 of A Student's Guide to the Schrödinger Equation. As I mentioned in the Chapter 3 introduction, the discussion of the Schrödinger equation in that chapter didn't use much of the mathematical background discussed in Chapters 1 and 2. And there's a good reason for that. It's because the discussion of the Schrödinger equation in Chapter 3 relied heavily on the wave mechanics approach to quantum mechanics developed by Erwin Schrödinger, while the concepts and mathematical techniques in the earlier chapters pertain more directly to the matrix mechanics approach developed by Werner Heisenberg. Both approaches lead to the same conclusions, but if you're planning to study quantum mechanics at the intermediate or advanced level, I think you'll find it helpful to have some understanding of both wave mechanics and matrix mechanics. So, both approaches are useful, but neither directly answers the question, what exactly does the wave function psi represent, and what happens when you make a measurement of a quantum observable? After almost a century of development, there's still no universally accepted answer to those questions, which is a source of profound embarrassment to some physicists. The most widely accepted explanation of the meaning of psi comes from the Born rule, in which psi represents the probability density amplitude. Amplitude because you have to square it to get probability density, and density because you have to integrate it over the range of interest to get the probability. You can read about the Born rule in section 4.1, where you'll also find a quick overview of each of the major tenets of the Copenhagen interpretation, including wave function collapse, the uncertainty principle, the correspondence principle, and complementarity. After that discussion, you can read in section 4.2 about the nature of quantum states and quantum wave functions and what each of those terms means. But you should be aware that some authors use these terms differently and some use them interchangeably. In that same section, you'll find a discussion of quantum operators and an explanation of several common misconceptions about quantum wave functions and operators. The general characteristics of quantum wave functions are described in section 4.3. I say general characteristics because if you want to know about the detailed behavior of a wave function, it's necessary to know the potential energy in the region of interest. You can see 3 examples of that in Chapter 5. But before getting to those specific potentials, I think it's very important for you to have a good understanding of Fourier theory. So you'll find a detailed discussion of Fourier synthesis and Fourier analysis in section 4.4. Fourier theory is applied in section 4.5 to position and momentum wave functions and operators in both position and momentum space. And of course, the last section of this chapter has a set of problems for you to work. And I think you'll find these problems both challenging and helpful. Thanks, and good luck.